Welcome back, students. In the previous session, we discussed what a relation is: a connection between elements of two sets defined as a subset of their Cartesian product. In this session, we'll take this idea further and understand the different types of relations we encounter in mathematics. These types help us classify how elements of a set relate to one another. All of them are defined within a single set, say set A, where the relation is a subset of A into A. Let's look at each type one by one. Let's start with the simplest type, the empty relation. An empty relation means that no element is related to any other element, not even to itself. Here's an example. Let A be the set of all students in a boys' school. Now define a relation R as A is the sister of B for A and B in A. But wait, the school only has boys. So, no such pair can exist. That means this relation contains no elements at all. It's an empty set. Written as phi, we write this as R equals phi, which is a subset of A into a. So, R is a subset of A into A, but it contains nothing. That's what makes it an empty relation. Now, the opposite of the empty relation is the universal relation. In this case, every element is related to every other element, including itself. So the relation R is equal to the entire Cartesian product multiply A. For example, if R is defined as the difference between heights of two students is less than 3 meters, this will always be true. So, R equals a multiply A. This makes it a universal relation. In simple terms, for a relation to be reflexive, every element in the set must be related to itself. That means, for every A in set A, the pair A and A must be part of the relation R. Let's look at an example to make this clearer. Suppose we define a relation R equals set A, B, and A is equal to B. Now think about it, A is always equal to A, right? So naturally, for every element in the set, the pair A and A will be included in R. And that's exactly what makes this relation reflexive. Now let's look at symmetric relations. A relation R is said to be symmetric if, for every pair A and B in R, the reverse pair B and A is also in R. Let's make it simple with an example. Suppose R is the relation A and B live in the same locality. Now think, if A lives near B, then of course B lives near A too. So if pair A and B is in R, then pair B and A is also in R. That makes it a symmetric relation. But here's a counterexample. Let's say R is defined as A is the father of B. If pair A and B is in R, A is the father of B, can we say that B and A is also in R? No, we can't. So this relation is not symmetric. To sum it up, in a symmetric relation, the direction of the pair doesn't matter. Let's talk about the transitive relation. A relation R is called transitive if, whenever set A, B and set B, C are in R, then set A, C must also be in R. Let's see this in action with a simple example. Suppose R is the relation A is greater than or equal to B, B is greater than or equal to C, then we know that A is greater than or equal to C. That's just how numbers work. That's a transitive relation. But here's a case that usually isn't transitive. Let R be the relation A is a friend of B. So, A is friends with B and B is friends with C. But does that mean A is friends with C? Not necessarily. That's why the friendship relation is usually not transitive. Now here's something powerful. What if a relation is reflexive, symmetric, and transitive all at once? Then it's called an equivalence relation. Let's take a great example from geometry. Suppose R is a relation on the set of all triangles, where R equals the set of all pairs T1, T2. It means T1 is congruent to T2. In other words, T1 is related to T2 if they are congruent. Now let's check. Is it reflexive? Every triangle is congruent to itself, so yes. Is it symmetric? If triangle T1 is congruent to T2, then T2 is also congruent to T1. So, yes again. Is it transitive? If T1 is congruent to T2 and T2 is congruent to T3, then T1 is congruent to T3. Perfect. So, this relation checks all three boxes, which means congruence of triangles is an equivalence relation. And that's what makes equivalence relations so special. They group elements that are essentially the same under some rule. Let's wrap up with a quick recap of all the types of relations. A relation is called empty when no element is related to any other. That's R equals phi, a subset of A into A. A universal relation connects every element with every other. R equals A into A. A relation is reflexive if every element relates to itself. Set A belongs to R. It is symmetric if swapping A and B keeps the pair in the relation. Set A and B in R means set B and A must also be in R. It's transitive if linking two related pairs leads to a third. Set A and B and set B and C in R must give set A and C. And when a relation is reflexive, symmetric, and transitive all at once, it's called an equivalence relation, capable of dividing a set into clean, non-overlapping groups called equivalence classes.